Mathematics, Hanoi, Vietnam. So his talk is about metric properties of certain fidelities. Yeah. So please, your time. Talk.
Okay, thank you very much for inviting me to talk here. He's a John work from this.
We don't hear you very well.
Oh, yeah, is it okay?
Yeah, it is better. Yeah, maybe please be
Okay,
closer to the microphone. Yes.
okay. So, uh, it is a John work with the whole beyond we still we uh, we use we start.
I don't hear you, Tom.
Can you move the next slide?
Yeah, I don't hear you very well. Please be closer, like or you might turn off the web camera so that the connection would be
Okay,
better. Yeah.
okay. Is
Yes.
it
Yes.
okay?
Yes. Yes.
We start to study this problem about the last year and would study the fidelity of on the quantum space. So there are many properties that study the fidelity. One we are interested in predict. So in this talk we will talk first about quantum fidelity. But then we study the different function with use this our matrices with
Uh, I'm sorry again. I don't hear you pretty well. I don't know what happened. Maybe all people hear you well.
is it okay?
No, I can't hear either.
Oh,
So please
what happened?
just keep microphone close to you. Okay.
Uh-huh. I
Probably
usually
because of the internet connection.
okay, is it okay?
Yeah, it is okay. But when you start talking, maybe you move far away from the microphone. So
Okay, so I have to keep about a couple of centimeters from the computer. Okay, so in this talk, we will discuss about the quantum fidelity. The original definition of the fidelity is by Josa. And then we are interested in the metric property of this functional first induced by fidelity from any in general. And the last we state the main reason about when the for when the functional induced by fidelity is a metric on the quantum space, and also we study the metric property that function by positive definite matrix is the largest space. So quantum fidelity is just a measure the state of this kind. It's like it's not really a metric because the fidelity they measure the similarity of the two quantum states. What is the similar? Similar in this sense is the two quantum states. They are identified, then the fidelity must be one. And the farther the quantum is, then the fidelity is closer to zero. state is just vector finite dimension. That's first. So it means that it just quantum state just vector in n dimension. N dimension.
Excuse me, I can't hear you.
Oh, okay. What happened? Let I check. I usually maybe for the Microsoft Team problem with Microsoft Team. It's a long time I haven't used it. Maybe.
No, so now I hear you well, but you know when you start presentation, I cannot hear you.
Oh, how bad. Okay, so okay, I repeat again. Maybe slowly. Is it all right?
Yeah, it is good now. Yeah.
Okay. So the quantum fidelity is the fundamental concept in quantum information. They measure each kind of the measure to measure the similarity between the quantum state. So what does that mean? The similar here. The similar means two quantum states are very close. Then the fidelity of them must be close to 1. And if the farther it means it's two different the quantum state, then the fidelity is like close to 0. That means the similar. A quantum fidelity was first defined by Ullmann, and then it's just the generalization of the probability concept that is between two Bure states. So a Bure state here we mean a unit vector in the space of n dimension, the complex vector space n dimension. So we mean that the Bure state is just identified with the vector with n coordinates, and its coordinate is just the complex number. That is the Bure state, and is so for a mixed state, they identify with an n by n matrix with a positive semi-definite and the trace beyond. So the mixed state identify with like complex set in the space of the matrix of order n. So later Chosa defined fidelity is just a two variable function, real value function. Or we can stay on the matrix space. But actually, the fidelity just defined only on the quantum state space. I usually say quantum state space means the space of on the mixed state. It means that the space upon positive semi-definite matrix with the trace 1. So Chosa proposed a list of axioms with the fidelity should satisfy. The first Chosa axiom I denote by saying 1 means the value of the fidelity between two quantum states quantum state is the value is between 0, 1, and it's equal to 1 if and only if the two states must be identified. So it is like somehow opposite with the matrix. And the second axiom here is I denote by J2 on the symmetry property in the value of the the value of the pair quantum state does not depend on order. And the third axiom here is noted by J3. It just means that the, the fidelity of two mixed states equals the trace of the product of two that state if one of them are pure state. This means that the fidelity of the two positive semi-definite matrix trace 1 equals the trace of product of them if one of them are projection, rank 1 because the fidelity origin like the inner product when the S day fixed state in that the S day the positive semi-definite trace 1 is the last is in the fidelity is invariant under the unit. So that the four axiom they also have some more maybe, but most of the fidelity they certify this or maybe just only couple. It depends. But the original like the Josa fidelity they said later the many fidelity just certify only the fee, not all. So the most famous is as I say is the Josa fidelity, but they are just the trace of like the Bures fidelity is related to the Bures distance. So that's why they also name the matrix induced by this fidelity, which usually say F1. The matrix induced by this fidelity usually called rest distance, rest angle. Measure vector or the side distance. We are interested of three function. First, rest angle is accord rest distance. That's already many and that is just the side distance function. So why this function is well defined? Usually the fidelity is the value of the fidelity is 0 and 1. So the square root of that fidelity also is 1. So the first axiom must be but
Oh my.
sorry.
Tong, could you please, be closer to the microphone again?
Okay. I use my computer only, no microphone, because my phone is, when I give a lecture I never use microphone. That's why maybe students didn't understand and they didn't say anything. Okay, anyway, I don't have a microphone here. I use directly to my computer only. Okay. So There are another fidelity they also discussed about. I introduced this fidelity in the paper by maybe in the first paper in the reference list at the last of this talk. You can see the paper. This is appear in the Journal of Physics. So they also have some fidelity like the super fidelity Fn. This somehow the trait of the product of two mixed quantum state, and then they also blurred with the another is how far the trait of that state to one, and also the fidelity induced by the super fidelity. Somehow they multiply with the dimension r. The number r here is just equal to 1 over 1 over n minus 1. Here n is the size of the matrix. We also say the dimension of the space. So here also the name is A fidelity. That is the trait of the square root of the two quantum state, and then they also power 2 of that constant. And also there are another quantum Chernobyl. It's just related to the mean of the trait of the. Oh, this is just the lower bound of the quantum Chernobyl. And we also define some fidelity like the norm-based fidelity, which is related to the trait of the product of two quantum states, and they divide by the maximum of that trait. And the two Hilbert-Smith fidelity, this is usually they call this is the Hilbert-Smith fidelity because it's very related to the Hilbert's product of two quantum state space. It is defined by well, it's just somehow it original it from the product of two quantum state. The product of them is not the trace of the two product of two quantum, then divide some function that usually they name that's fidelity. So here on the list of the fidelity we will discuss it. Okay. And the question we want to answer in this work is when the modified Bures angle across is the matrix or the modified Bures distance and modified sine distance when they are matrix on the quantum state space, that's first, and then when they are matrix on the state of the space of positive semi-definite matrix, put in non-zero, we usually define non. So we already answered this question. The question, well, then this property already studied in the work in the list of the reference in the paper beside number 3, and here is the table of the matrix property they already studied. So here the cross or the check mark. The check mark here is the mean. The metric property is well is for example here the first line F1, the across of F1 means the modified Bures angle of F1 is metric, right? The check mark. And also for modify Bures distance also metric, and the modify angle here also metric. For the second line F2, then the modify Bures angle is not a matrix. They have a counter. And also the modified Bures distance of F2 is also not a matrix, but the modified Bures angle is similar for the for, for the quantum check about. They also have a they are not a matrix at all. For the Fn, the super fidelity, only the modified Bures angle is a matrix, and the other two will not. But for FC, C is just defined by the fidelity, and they add some constant R. They related inside, and it's still a mystery to me why they interesting. So they still open question here in that they still don't know if it's matrix or not for modified and modified rest angle. They already saw that in FC, the matrix of the modified rest angle is side than it. They are all studies it. I remind, is it matrix of the study on quantum state? In that, on the state of positive semi-definiteness with phase one only. For the geometric mean, for the geometric fidelity, they show that at this side is but the other two FAM also. But for F of AM, the fidelity here, they say they still don't know if the modified with side distance is matrix or not. But they show that the other two is not matrix like they have here. Or the last is the last slide they show already like modified distance is matrix side distance. But the other left is not, they still don't know. So in this work, we try to answer 4 question marks here. And in that we answer for this matrix property called the quantum state. And then at the end, we answer extend this property positive with penetrate. For the first observation, we had to take a look at the table. Here, also from the table we guess maybe the modified first angle is matrix and the other one. But if side is not and the other, that's why of the modified first angle is strongest. If it's matrix, then modified first and if modified is matrix, then modified side is
Tong, would you please closer to the microphone of your laptop?
Oh, I see. Okay. Is it okay?
Yes, it is much better.
Okay. So, for the first observation, we saw that
We just totally lost your voice.
Oh, sorry. I happened. I already closed, but what happened to my unit? So I say if the modified side distance is not a matrix, then we automatically imply that the two other is not a matrix. One thing here, I didn't say it's a matrix on which space. We are studying on two space. First is quantum space. In that the space upon positive semi-definite matrix space 1. The other space is the quantum. The other space is the space upon non-zero positive semi-definite by any condition trace that non-zero.
Yeah, we don't hear our speaker.
Oh, you
What?
can hear too?
Yes,
What
you know.
Sorry. What can I say? What can I do?
Maybe the internet is not really good.
Good. I didn't use Team very often. That's why maybe.
I don't think that is a problem in team. Maybe just about the internet. But you know, sometimes it's clear to hear you. But yeah, but when you start talking, maybe you move far away from the laptop. So that's why.
No, I still keep very close to the.
Okay, now it is okay. Yeah, just yes.
Yeah. Oh, what happened? Okay, so I repeat again. The first observation from the table 1, you may realize that the modified Bures angle is stronger than the other, and the modified side distance. Then from that observation, we complete one. So in order to consider these three metric properties, we first study the modified angle. And as you see from the one, if modified Bures angle is vertic, then the other two must be vertic. Here, a metric here, I just mean in general. That maybe in they are metric on the quantum state space or also on the space of on positive semi-definite matrix. So they are both space are okay. So the main theorem here is we already published on the quantum. We confirm, we answer on 4 question marks in the table. The first is the modified Bures angle F1 is vertic on the quantum state space or the space of mixed state. Or another way to say it is the matrix on the space on positive semi-definite matrix with space 1. We also answer the second question, modified Bures angle across of FC answer. And the modified Bures distance, the root of 1 minus the answer quantum state. And the last is the modified side distance, 1 minus. So here, actually, we do the first, right, for FC, the metric property of the functional induced FC, we just modify the angle, and the other is the angle. So the idea of the group here from phi d phi. Okay. Sum of x minus the group 1 this function and graph.
We don't hear you at all.
Oh, sorry.
I don't know, what happened with your laptop, but it seems like
Oh,
we have hard time.
very difficult. So the key thing in this work, we study the function phi as we define on the first line of the slide. This function is we study the geometrically of this function, and even we try to sketch by the maple in order to understand how this function works, and then we try. Okay, so from that property of that function, we come to the lemma 1. Lemma 1 is just the key lemma, but the proof is very elementary, very elementary. So here we suppose that F is the fidelity, satisfies the first two axioms. Axiom means that the value of the fidelity must be 0 and 1, and it's equal 1 if and only if the two variable must be identified. And the second is about the symmetric of the function. So the modified Bures angle cos of square root of f is a matrix on the mid quantum space if and only if the function f, the function phi defined above, must be non-negative for every ABC, where x is just the value of the fidelity of A and B, y is just the value of here this that y equal to f of BC, and this is the value of f at A and C. Right? Actually, the first two axioms of the matrix is well defined. I mean, the accord here is non-zero, and it's equal 0 if and only if the accord of A and B equal. If A and B equal, it will be A equal B. I mean, the two matrices must be identified if the value of the accord is 1, is 0. Sorry. So the first two property of the matrix is well defined automatically. So in order to prove the modified Bures angle is a matrix, we just want to show that this function satisfies the triangle property, the triangle inequality. That's why we given here any ABC or arbitrary ABC as the mid quantum state, then we have to show that the accord of square root of f must satisfy the triangle inequality related to ABC, right? So in order to prove this, I just give only very few idea here, and it's elementary. So first you have to show that the accord of square root of x minus accord square root of y must be less than or equal accord of z, and also less than or equal accord of square root of x plus accord square root of y. Okay. So first, this is from the the definition of the accord and the definition of the triangle inequality. We can come to the inequality 1. And so in maybe just okay. So the second inequality phi is less than equal 0 if and only if, then well, maybe on my computer they the last line not appear. Maybe okay. Anyway, the last line of the previous slides, how to obtain the last line of the previous slide. Well, you just consider the function phi is just a quadratic in the variable square root of z, right? You consider it a polynomial of degree 2 in square root of z. It means that if you let t equals square root of z, then the function phi here is just the quadratic in t, and then it's less than or equal to 0 mean by the discriminant uh, uh, must be negative someone, and then and so on, and then you can factor it out, and then you solve it, and then you obtain that the last line of that slide. Okay. Okay, so can you move on? Okay. So the second lemma we usually use is just the gram matrix must be positive semi-definite. So in order to show that the modified Bures angle satisfies the triangle inequality, we must show that the gram matrix defined in the second condition of lemma 2 must be positive semi-definite, and it's equivalent to show that the across of F is matrix. As I say, the those axiom J1, J2 ensure that the df, the function df, satisfies the first two conditions of the matrix. The only left is the triangle inequality. So the third equivalent property is just the function s, but actually I should say the function s here is just the function phi, but for x square, y square, and z square, so it is different. The function phi only that. Right? So the function s and the function phi is very similar. If you sketch the graph, then the function s like how it's move a little bit because it's square, right? Then the graph is a little bit bigger than the function phi, because the function phi only degree 1, and the function s here is somehow just a little bit square. Well, look at the marble, then you can see it a little bit different. I don't have a picture here. So. Anyway, in our argument, we usually use two functions for convenience. Okay. So could you move? Okay. That is the two key. The lemma 1 and lemma 2 is the key thing here to prove the first theorem. The first theorem, on the other hand, we also usually try to write the fidelity as the product of some vector, not really usual, but not very inner product of two vector, but very similar to inner product of two vector, and then we saw that the gram matrix is non-negative. That's the idea. So using the same idea, that we also study the super fidelity FT. So FTC here is just a linear combination of the convex combination of the function constant 1 and the FC. As you know that FC is the induced matrix, only modify Bures angle only. Right? So here we also study only the and we define the general. This is the general line of the super fidelity and FC. Right? So when the t equals 0, it's a come back to the super fidelity, and when t is the dimension 1 minus r over 2, well, this is for FC at in the first theorem, and in the paper list in the number 3 of our later. So we use the same idea but different proof, different argument, but the same idea of the previous theorem. We also can show that the modified Bures angle of the fidelity FTT are metric on the quantum state space for all t between 1, less than 1, and bigger equal r. So what is the esteem case here? As we saw that the modified Bures distance, and so the across means the modified Bures angle are not a metric on the quantum state space. Right? So if f equal fc or fn, and the other remark here is the limit of the number 1 minus r over 2 equal half when the sign of the metric tends to infinity. In our theorem here, we don't mention the sign n. So this theorem true for every sign n, right? So that's why this guy very critical here. So, but unfortunately, our question here for fixed number n, for example, fixed sign of the matrix n, then the number r 1 minus r over 2 may be less than half, sure. But we still don't know what is the counter example if the FCT in that case will be not a metric or a metric. We just rule that it's a metric for any side of the metric, but for particular side of the metric, maybe we get the number t here is lower than half, maybe, but we don't have a counter example, and we also don't know how to do it. So that's still maybe not very interesting, but it's still unclear for us. And we think it is very, very, very critical, very extreme result already. Okay. So would you? Okay. The next topic is we try to extend the property to the space of all positive semi-definite matrix with a non-zero. We denote by P the space of non-zero positive semi-definite matrix. So it's larger than the quantum state space Mn, and we pay attention to only the fidelity which we name Hilbert-Smith fidelity. Oh, this name may not belong to us, belong to the work of the physicists in the list of, in the reference number 3. We will see later. So the fidelity here we rewrite in the formula 3. It's a little bit different from the original definition by Liang and other in the footnote reference here, because in that paper they f of f they divide by the trait of AB divided by the function of trait of A square and trait of B square. A little bit different, just only we write multiply by the function f, and then they divide by just only that. Mean the function f we write here is just 1 over f of that paper, but nothing different meaning. That only different in notation. So in particular, when the function f lies the ratio between the geometric mean and the arithmetic mean, then f of f is just the f of am. It's very important. You already know the property about the fidelity of FAM in the previous slide, right? And we already studied the metric property of that fidelity. If the function small f is constant 1, then it's induced the fidelity like GM, the geometric fidelity, like before. So if the function f is just the ratio between the geometric mean and the maximum mean, then it's just the f2 to the well, f2 in that work they write the number 2, but here I write the double I for different 2. I mean, for not misunderstand that is a constant function 2. So that's why I write it for avoid in the case that people understand that the small f is. So that is when we look back to the famous reality before, so they including some famous reality like AM, GM, and okay. Okay. So so here we also remark here the modified Bures angle accord of f of GM, the geometric fidelity. They certify the triangle inequality on the state of positive definite matrix. But unfortunately, it is not a matrix because why? Because the they equal 0, right? The accord of f of GM equals 0. It cannot imply A and B are the same. The two matrices are just multiple, mean linearly independent, linearly dependent. This matrix is just multiple of the other. But when you fix the tray equal 1, then they must be identified. But if you don't fix the tray equal 1, then they are not identified. So that's why the modified Bures angle of the geometric reality FGM is a not a matrix on the whole positive definite space, but it's a matrix on the quantum state space. The other modified Bures angle here we also mentioned here is a matrix on the whole space of positive definite matrix. But if you take square root in the modified Bures angle accord of square root of f2, then it's not critical even on the quantum state space. So that is, if you take a square root, then it's more difficult to obtain the triangle inequality. Well, okay, so we also found an interesting that the modified Bures angle of the fidelity induced by the ratio between the harmonic mean and arithmetic mean is a matrix on the positive definite matrix space. Here, as you see, I write the notation harmonic mean and arithmetic mean is just a ratio. As the corollary, in order to prove of that theorem, that result, that presented, we first apply the lemma 2. We obtain that corollary here. In that diagram matrix induced by the small f, function f, is positive semi-definite for every number x, y, z between 0 and 1, then the modified Bures angle across f of f is. Now that I write here, I write in the second part a little bit. Right? In the first part of my talk, the modified Bures angle across of square root of f. Right? We have square root here. But in the second part here, we just study only across of f, easier to obtain the triangle. So that's why, in some case, in the first part, if you take the square root, then the modified Bures angle across square root may not be a matrix. Exactly, it may not satisfy the triangle inequality. But if you remove the square root, then it may satisfy triangle inequality. The reason why, like as I said before, well, sometimes if you remove, then the graph of the function phi is somehow a little bit slightly different. That's why it's said. Okay. So that the color, this color is heating, and apply this color, you obtain the second color. When you given any mean smaller than or equal geometric mean, then we study the modified Bures distance of the fidelity used by the ratio between mean m and the arithmetic mean n. Then it's a matrix if and only if this inequality is satisfied, where m1 is just a single variable function induced by the two variables of m. When we study, when you substitute first. So this is the way we obtain. There is one correspondence between the monotone function, non-negative monotone function m1, and the mean between two positive number m. So this is obtained from the Drummond matrix mean property. Okay. Represent the mean of usually we use the last color here in order to prove something here. You use two inequality here in order to prove something in matrix. We multiply by the, well, we change to consider the polynomial inequality. Right? When you change to the polynomial inequality, you can use the optimization min max value on this set. Unfortunately, set S and T here is just the first part of the lane. S so sometimes we may use HS2 and the infinite. I think for given any particular, we can check if this inequality is satisfied now. But in general, then means here. So that's why we just apply for particular mean line. M is just harmonic, max. That's the particular mean, not general mean. So for general mean, you cannot classify.
Hello.
Yeah. So could you?
Yeah, I think it is the last slide of the talk, right?
Okay. For the net, is just the reference. So could you move to the reference? So for the reference here, as I usually say, the paper number 3 is the main paper we studied. So when we first actually we saw on the seminar organized by Hua here, he introduced our Bures distance, and this come to us to study the quantum fidelity matrix number 3. And yeah, well, as I already informed, the answer for the open question in that paper, and we try to extend that is the space of one positive line paper.
All right, thank you so much for the talk. Yeah. Sometimes we don't hear you, but sometimes we hear you well. All right, so do you have any questions for our speaker? Okay, we don't have any question, but actually, you know, I just want to make a short comment about this. Like, you know, when you consider distance between two quantum objects, that is nothing but, you know, the distance between two equivalent classes. In here, yeah, we use, since we consider positive semi-definite matrices, and quantum orbit kind of, you know, with that they will consider some all matrices or positive semi-definite matrices, right, which are similar, right, with each other to some, you know, unitary matrices. So that means if we have another equivalent classes or equivalent relations, so we would have another distance, right?
Well, for the fourth axiom, only one.
We don't hear you, Tong. Yeah.